These two retail barcode numbers differ by 1 digit. The first passes its built-in check. The second does not. That final 3 is not just one more piece of product data. In this EAN13 example, it is calculated from the 12 digits before it. Change one of those digits, and the final answer may no longer fit. So how can one tiny number notice a change somewhere else? To answer that, we have to separate 4 jobs that a checkout scan can make look like one instant, and one boundary matters from the start. This is a different standard from the baggage barcode in the previous story. We are looking at EAN13, one member of the EAN and UPC retail family. This is not a rule for every barcode. First comes the optical structure. A reader does not begin with 13 trusted numbers. It begins with light and dark modules, clear space around the symbol, and guard patterns that frame groups of encoded digits. Each encoded digit occupies 7 modules, selected from defined pattern sets. The character patterns are self-checking, and the symbol is designed to be decoded from either direction. Those features help turn the printed pattern into a sequence of digits. If the spacing, contrast, structure, or character pattern cannot be decoded, the process can stop here. The final digit is not repairing missing bars. Its job begins after the reader has a candidate number to test. Now, the rightmost character becomes special. In EAN13 and UPCA, it encodes the check digit. The reader can verify that digit automatically during reading and decoding. Here is the complete arithmetic using GS1's public numerical example. The first 12 digits are 629 104 15 0021. The final 3 will stay outside the calculation for now. Start at the right edge of the 12-digit body. Multiply that digit by 3. Moving left, multiply the next by 1, then 3, then 1, alternating all the way across. The products are 6, 6, 9, 3, 0 to 12, 1, 15, 0, 0, 2, and 3. Add them, and the total is 57. The exact pattern looks busy, but the reader only needs the result. The rule chooses the amount needed to reach the nearest equal or higher multiple of 10. After 57, that target is 60. 3 more completes it. That is why this number ends in 3. Now repeat the opening change. The last body digit flips from 1 to 2, but the old check digit 3 stays where it was. Because that position has a weight of 3, the weighted total rises by 3, from 57 to 60. A total of 60 already lands on a multiple of 10, so the required check digit is now 0. The printed 3 no longer matches the calculation. The pattern can still be structurally encoded, but its whole number fails this check. Under the EAN and UPC rules, a reader can reject a mismatch during decoding. But that does not mean every failed scan reached this stage. Bad printing, damaged structure, poor contrast, or other decoding problems can stop the process earlier. The single-digit result is stronger than one convenient example. Our deterministic model changed every position of this 13-digit number to every other possible digit. That created 117 single-digit substitutions. All 117 failed the check. The reason is compact. Change one body digit and its non-zero difference is multiplied by either 1 or 3. Under this modulo 10 rule, that change cannot disappear, so the expected final digit must change. Change the check digit itself, and it no longer matches that expectation. Detection is not correction. The check tells the system that the supplied number and its final digit do not agree. It does not identify which digit changed, reconstruct a missing bar, or tell the reader what the intended number was. Watch what happens if we replace the old final 3 with the newly required 0. The number 62910415000220 now passes the arithmetic, but we have not proved that this identifier was allocated, that it belongs to any product, or that a database contains it. We have only made the composition valid. Price, description, ownership, and other product information are not hiding inside that final digit. Those belong to separate records and systems. A passing check only says that this number satisfies its arithmetic relationship. It does not say what a later lookup will return. The check also has deliberate limits inside the number itself. 2 changes can offset each other. In our model, changing the first 2 body digits turns 62 into 04, while leaving the weighted total at 57 and the final 3 valid. The check passes, even though the body is different. Adjacent swaps reveal another boundary. Across the model's 90 ordered unequal digit pairs, this check caught 80 swaps. It missed 10, all involving digits that differed by 5, such as 1 and 6 trading places. Compact checks trade certainty for speed and simplicity. That gives us the complete system. First, the printed modules have to be found and decoded. Second, the resulting EAN13 digits have to satisfy their required check. Only then can a separate application use the identifier to request some other record. Each layer answers a different question. So why is the last digit different? Because it is a compact arithmetic receipt for the digits before it. In this EAN13 example, 3 completes a weighted total of 57. Change 1 body digit, and that receipt no longer matches. It can expose an error without knowing the correct product, price, or identity. QR codes use a different error correction system that can recover data after some modules are damaged. Next, we will cover an original QR code and measure what survives.